So let's continue from here. So the axial diffuser with length n and the diffuser will wall length is L, and the inclination angle of the divergence angle pi W is given here, and the flow condition from point 1 to flow condition point 2 is here. What is something? So as you see here, there is a small differential length dx, because x is our flow direction. So you can take this strip of finite length, which is dx. Okay, and area at the first point here is a, and area at the second point is a plus dA. And now the thermodynamic relation of the TS diagram is given here. So that TS diagram represents various points. Point 1 is here. Okay, point 1 that depicts the condition of point 1 on the diffuser. We have point 2 somewhere around there. So T1, T2, the total pressure T1 and total pressure T2 are equal here. Okay, and the velocity term V square, V2 square over 2Cp is there. We have V1 square over 2Cp. So this Cp is the specific heat at constant pressure condition. Okay. And the change in entropy, delta S, is here, from here to here, ds. Okay, so that is given. So this is just a subsonic diffuser with TS diagram, which depicting the static and the stagnation state in the diffuser. So what it tells us, the static pressure rise, P2, which is greater than P1. So we can observe it. P2 is here, the static pressure. P1 is here. Okay. This curved profile indicates the P1 and the P2. Again, the total pressure PT2 and the PT1 are here also. Okay. So P2 greater than P1, which is accompanied by static temperature rise in diffuser. T2 is greater than T1. As you see, T1 is here, T2 is here. So T2 is greater than T1, P2 is greater than P1. That is from this diagram. And also, large inlet kinetic energy is shown in the figure 2. So the inlet kinetic energy is represented as V1 square over 2Cp. This is the amount V1 square over 2Cp is from this point to this point. That is the large value, which diminishes to small kinetic energy at the exit. So the exit condition is represented with 2. So V2 square over 2Cp is this amount only. Okay, it is this amount. Okay. This is the kinetic energy at the exit. And this is the kinetic energy at the inlet. Okay, it is large. So the flow's stagnation enthalpy remains constant in adiabatic diffuser as a constant total temperature pressure, because the total temperature is constant here. That is adiabatic condition. Okay. Finally, the total pressure at exit of diffuser is lower than the inlet, which is the basic of the enthalpy rise, delta S. So we can relate the static pressure recovery coefficient, CPR. Okay, that the static pressure recovery coefficient is given with P2 minus P1 over Q bar. So we know that Q is equals to half rho V square. Q means dynamic pressure. These two are static pressures. P2 and P1 are static pressures, and Q is the dynamic pressure here. So it is a unitless quantity, non-dimensional pressure. So P2 minus P1 is change in pressure, and the dynamic pressure is density times velocity square over 2. So this is a static pressure recovery coefficient. Okay, and now by applying the Bernoulli's principle between station 1 and 2 of diffuser for unviviscid fluid, and using the continuity equation for the one-dimensional flow, we can relate the ideal diffuser performance, CPR ideal. Anyways, this Bernoulli's equation tells us the expression of the Bernoulli's equation. Let me revise it once. It is just P1 plus half rho V1 square, which is equals to P2 plus half rho V2 square, considering the elevation, the same elevation. Okay, so that is the Bernoulli's equation. Again, the continuity equation is also restated as mass flow rate m dot is equals to rho area velocities, area times velocity. This is called the continuity equation. Okay. So for one-dimensional, we have this kind of relation only. So CPR ideal is given with Q1 minus Q2. This is dynamic pressure. So, and also we incorporate it with area ratio. Okay, Q1 minus Q2 over Q1. So which gives us 1 minus Q2 over Q1. And applying this, the mass flow rate and the Bernoulli's principle, finally what we can get instead of Q2 over Q1, we can get area 1 over area 2 square. So this is called area ratio. Actually, 1 over area ratio, because if it is A2 over A1, it is just area ratio. So that 1 minus 1 over area ratio square. So area is just diffuser exit to inlet area ratio. Okay, A2 is the exit area, A1 is the inlet area. Okay, and AR is equals to AR, area ratio, AR is equals to area 2 or exit area divided by area 2 over area 1. Okay, that is diffuser exit area to inlet area ratio. So this equation shows that for a very large area ratio, ratio diffuser, the ideal static pressure recovery will approach to 1. For example, if the value of the area ratio here is big number, 1 over big number gives nearly 0 result here, so that we have left 1 only. So the ideal pressure recovery will be nearly 1 during that time. Okay, so we can observe it from here. the diffuser pressure recovery as a function of diffuser area ratio. So we have from 0 to 1 here in the vertical axis, ideal CPR is there. And in the horizontal axis, we have 0 to 5 is plotted. The area ratio 1 that indicates if the area ratio is 1, what happened? This thing is 0. 1 over 1, 1 minus 1 over 1, which is 0. If this square, the area ratio is 2, what happened? 1 minus 1 over 4. If it is 3, 1 over 9. If it is 5, it is 1 over 25. So that we can calculate CPR ideal from this diagram only. So, for example, for 1.5, we can find this amount. You can trace it back from this plot. This indicates for area ratio 1.5. For area ratio 2, we have this value. For area ratio 3, 2.5, we have this value. For 3 also, okay, when we approach to 5 and more number, it becomes nearly 1. Okay, so this graph indicates the ideal CPR versus diffuser area ratio. Real diffuser and their stall characteristics is another topic. So on that, we consider here the real flow environment with boundary layers are formed and have a tendency to separate when exposed to rising static temperature pressure, which is known as an adverse pressure gradient. So here we consider an adverse pressure gradient. And the behavior of the diffuser to be driven by the viscous region near it is walls. Therefore, the performance of the real diffuser is strongly dependent on the inlet boundary layer condition. And the geometry of the cross-section, as well as the center line curvature of the diffuser influences the cross-flow boundary in the boundary layers. Okay, so these are some of the real diffusers. 2D rectangular diffuser is here. Okay, another is axial axisymmetric diffuser, which is called conical, and this is annular. So on the annular, we have this kind of diffusers. So these are just simply subsonic diffuser geometries with a straight center line. So the center line for all of them are the same as straight. So subsonic diffuser exhibit 4 different flow regions or stall characteristics. And the flow regions are tied to quality of exit flow. So the and different flow regions are of interest to an aircraft inlet designer, so that we examine them separately. So what are those 4 different regions? Let us see. Line of first stall is here. Line of appreciable stall. Again, large transitory stall, and then fully deployed 2-dimensional stall. And then finally it goes to hyperesis zone, and finally jet flow zones are there. So this is jet flow zone. Here is no actually below here, below the line of first stall, no appreciable stalls happen. So actually we can directly demonstrate it from here. Okay. So non-dimensional axial length of diffuser and the total divergence angle of the diffuser are chosen as the axis of our chart. So in this chart, we have 2 pi is in the vertical axis. We'll demonstrate what are those. Another n over wt is in the horizontal axis and provided with number 1 up to 60. And this is from number 1.5 to up to 100. So on the lower half of the chart, where the line is AA, line AA, the first line this is drawn, we note that a stable flow region. The flow, actually below this region, the flow is no stall is observed. Above line AA, that means we have line AA, then above that you have line of appreciable stall line here. Line BB is there. So this is BB. That line BB is the stall phenomena is recognized and characterized as transitory stall. So the stall here is line BB is considered fully deployed two-dimensional stall. And then above that, the beyond the transitory behavior lies the fully deployed stall will occur. So that actually, we call it as a stall here, but it is just the engine phenomena. So that more of the better word for that is the surge phenomena of the engine. ስለዚህ እነዚህን ነገሮች ከዚህ ማየት ነው። Another subsonic cruise inlet የምንለው ምንድን ነው? For the subsonic cruise application, the total flow deceleration is divided into external and internal segments. The external diffusion takes place outside the inlet, where the design capture stream tube acts like subsonic diffuser. So ይህን ለማሳየት subsonic cruise inlet ላይ ኤሪያ ሬሽዮ አለ፣ ማክ ነምበር ሬሽዮ አለ። So this A note indicates area of far stream, as you have learned in the last chapter. ይህን ነገር ባለፈው ቻፕተር ላይ ተምራችኋል። ፋር ስትሪም አለ፣ the flow far stream. One indicates the intake region here. Two indicates the fan or diffuser region. Fan and diffusers are around here, but one is directly the intake point. Okay, so far stream flow condition, the intake condition, because what we are talking is inlet, so one indicates the inlet condition. So this formula, Mach note indicates the Mach number at far stream condition. A note indicates area at far stream condition, so that A note over A1, which is equal to Mach 1 over Mach note, the whole. We 1 plus gamma minus 1 over 2 Mach naught square divided by 1 plus gamma minus 1 over 2 Mach 1 square. So this is the relation. So in the absence of, actually this formula works in the absence of shock that fortunated outside the inlet, and we consider here reversible adiabatic, which is called isentropic flow. Reversible adiabatic means isentropic flow condition. Okay. Okay, so here we have rho note, Mach note. Here we have Mach 1, pressure 1, pressure note. Pressure note means the ambient pressure, and pressure 1 is the static pressure at the inlet. Okay, so the flow condition is like, and Mach 2 here, pressure 2 is here. Okay, so even their values are also having some different shape you can observe. So the area ratio A0 over A1 is a function of external deceleration from the cruise Mach number. The cruise Mach number means the far stream Mach number to the inlet lip Mach number, that is M1. So M1 is the inlet Mach number. M0 is the cruise Mach number or the far stream Mach number, and is called the mass flow rate parameters. Okay, mass flow rate parameters. This area ratio is the mass flow rate parameters. Okay, so in the previous equation, this equation you can say, the equation is here. So on that, the various cruise flight Mach numbers in the transonic regions are given here. So we can observe, for example, the inlet Machs are given from 0.4 up to 0.7 on the horizontal axis. And the area ratio or mass flow ratio is given here. It is from 0.65 up to 0.95. And also, the cruise Mach is given as 0.8, 0.85, 0.9, 0.95. For that, we have different floats are there. Okay, different floats are there. So one can take, if I take my M0 is equal to 0.8, then we can take this line, okay, the line with square dots, and we can evaluate for different Mach. So let M1 is equal to 0.55, and then M0 is equal to 0.8. Then we directly trace like this. Let me trace it for let it be 0.6 is our inlet Mach number, and assume that our M0 is of 0.8. So I will go from here to this point to get the area ratio. I can get area ratio here. So that it is in between 0.85 to 0.9. Nearly it is 0.88, I can say, 0.88. So area ratio 0.88, which is equals to M1. M1 is 0.6, 0.6. M2, which I selected, is 0.8, 0.8 times. Then consider the gamma of air is 1.4. Okay, so 1 plus 1.4 minus 1 over 2 times M0. So M0 is already 0.8 times 0.8 square. So this is the way how you can use this diagram to calculate. Okay, the whole over 1 plus. So you can do like that. Just I'm giving you as example. So by that you can immediately calculate. Okay. So the inlet lip pressure, P1. This is the inlet lip pressure. So that pressure ratio, P1 to P0. So this is the cruise pressure. Okay. So what we can do, we can calculate it also. Again, the conservation of mass relates to area ratio to Mach number, so that this formula This is already stated here, this formula itself. So, okay, so the captured stream to engine phase area ratio from takeoff to cruise condition. This figure illustrates flight Mach number given here, area ratio here. So the takeoff point is somewhere and the cruise point is somewhere, nearly 0.9. The free stream Mach number, 0.9 is a cruise Mach number. Then what happened? So you can observe here, area 2, area naught is here. If we are flying around here during takeoff, so this figure illustrates the condition only. So the function of supersonic inlet is the same as the function of subsonic inlet to decelerate the flow to engine phase. Mach number requirements in range of 0.4 to 6 within the entire flight envelope, especially for the supersonic inlets. Mach requirement at 0.2. Actually, our 0.2 is our 0.2 is here, especially in the near to fan or diffuser. This is diffuser actually. And the flight Mach number ranges from 0.1 at takeoff to 0.95 at cruise. So that is this representation. 0.1 at the takeoff to 0.9 at the cruise is the flight Mach number. Yeah. So in practice, the flow diffusion from supersonic to subsonic flow involves some shock. Shock waves are there. So the supersonic inlet is very much dominated by shock interacting, reflecting, and shock boundary layers. So these are the phenomena that occur in the supersonic inlets. So this is the shock actually. This is the cruise Mach number, which is greater than 1 condition. What you can observe from here, mu naught is the Mach cone angle. Mach cone angle, okay? And behind of here, in the free stream, it was greater than 1. But after free stream, there is all compression waves happen. Then after Mach is now 1. Okay, it is sonic here. And it is perpendicular to the compression Mach waves. Okay, so the Mach angle is given with mu. The next important one is convergent divergent nozzle or CD nozzle, or we call it as CD duct. Isentropic compression ramps in a duct and subsonic diffusers to create CD duct applicable of decelerating supersonic flow to subsonic flow. This actually creates subsonic. Okay, so it can decelerate supersonic flow to subsonic flow, and reversely and adiabatically. Actually, in this case, it is duct case, but in the case of nozzle, it can work in opposite direction rather than decelerating, accelerates subsonic flight to supersonic flight. So let's consider the free stream condition 0, 1. Throat, TH indicates throat and 2 indicates exit. Okay, 2 indicates exit here. So in front of point 1, the flow is greater than Mach greater than 1. Okay, so that is at the captured free stream tube point. And once it reaches to the throat Mach number is 1. So that is sonic point. And once it passes the throat, in the case of diffuser, the Mach will decrease. But in the case of nozzle, what happened? In front of this throat, the flow is subsonic, and at the throat, the flow is sonic, and after throat, the flow becomes supersonic. So it is a reverse. Okay, so this is a duct flow, rather. So now let's consider an isentropic fixed geometry CD inlet, convergent divergent inlet. Okay, so inlet condition, which is discharged for MD is equal to 1.5. Calculate over speed Mach number that will start this inlet. So what are the solution here? Let's first establish the design area ratio. Area ratio A1 over area of throat. So that area ratio, Mach number of 1.5 is given. Okay. For the isentropic table, gamma is 1.4. We know. So we have area 1 over area of throat, which is equal to area 1 over area asterisk. This asterisk indicates the throat area condition. So which is equal to 1.175 as 62. So where can we get this? 1.1762. So let's come to this point. So relate this one. So on that 1.1 means which one? This is with plus sign 1.1717. 17 is this. This is 179. This is okay. So it needs some kind of interpolation. You see, from 1.12, this is 12. Sorry, 17 is here, 176. So this is the area ratio. So if the starting shock is at the lip, the subsonic flow at My will have the same A over A strike as the inlet. So AY means any arbitrary area. A strike is the area of that throat condition. Okay, so which is equal to this. And we convert isentropic. There is isentropic table on the book. We can check it later. The book, Farouk book, you can find such kind of transition. Because now, if area ratio is equal to 1.176, then from the isentropic table, with Mach less than 1 condition, My is 0.6. We have to refer it for the isentropic table that gamma 1.4. Actually, usually we use gamma 1.4, but on the book, for different values of 1.3 for hot gas, 1.25, 1.2, and different values of gammas are there. So from that table at page 911, you can find that. So My is the Mach that related with 1.76, area ratio 1.76 is 0.61. We can see also here it is 1.5 actually. Yeah, Mach actually given for us we traced it based on the Mach. This is the Mach number. So that is this Mach. So most of the parameters related here are our important parameters. Okay. So now for area ratio of 1.176, 1.176 to 18. So it is far away. So this, we have to make some kind of interpolation. This is 1.188. Our 1.176 is somewhere above here. Anyways, so we have to refer it. And once the Mach number of my is given 0.61, then appendix C on the normal shock table. On the normal shock table, we can check mx. My is given, mx is also be calculated. So look, this is M2 and M1, M2, 1.8 means here somewhere, 1.8. Okay, 0.61, 0.61 is area ratio. ይሄ ቴብሎቹን የማንበብ እንትን ይፈልጋል። የሆነ ጊዜ ሰተን ቴብል እያገላበጥን ማየት መቻል አለብን። አለዚያ እዚህ ጋር ልንቸገር እንችላለን። So once we know the mx 1.8 from that, what happened? M over speed is 1.8. That mx means m over speed. So exhaust nozzle design is also another important point which we are going to see. So designing objectives of modern aircraft exhaust nozzle, one is efficient expansion of the engine gas to the ambient pressure, now low installing drag, low noise, low cooling requirement, efficient thrust reversing, efficient thrust vectorizing, low observability, that radar hiding itself from radar, lightweight, low cost. So these are actually nozzle requirements. We already stated 10 requirements from the inlet design. Similar to that, the nozzle design also needs this kind of requirements. These are the design requirements for exhaust nozzle design. The main function of nozzle is to produce thrust, that what you call gross thrust. So the gross thrust is given with M9 V9. You know, this 9 represents the exit point in our previous chapter, times P9 or minus P0 times A9. So momentum thrust and pressure thrusts are called the gross thrust. So the gross thrust of nozzle is maximized when it is operated as fully expanded. Fully expanded condition means optimal expansion condition. So a nozzle is fully expanded when the static pressure in the